The supply chain issue has been raising the price of food and beverage industry throughout the world. Good morning, judges and committees. On this lovely occasion, we from the Tercio team from Universitas Indonesia will explain about our solution toward the supply chain crisis in food and beverage industry, and that is by building a sustainable carbon capturing fertilizer plant filled by plastic waste. My name is Jonathan Rako Briliwan, and this is my team, Muhammad Ryan Firas and Ivana Angelica Purba. This is our outline. We will start first with the introduction, continued with solution and design, location and economic analysis, then continued by risk, trade-off, and impact, and finally the conclusion. So we will first continue with the introduction and the explanation about the landscape and problem next. Here are our introduction. It is estimated that there are 8 billion humans in 2024, and the current new normal situation from the previous lockdown has created a shock in the supply and demand world, and therefore it increases the fertilizer by significantly and suddenly. Next. Not only that, politics and also environmental law has also created a disruption in the supply and demand issue due to the rising price, and politics has created an embargo toward one of the most important source of natural gas in the world, and therefore urea price skyrocketed, especially due to the need of natural gas for the production of urea, and it creates a food insecurity. Now we see a potential towards the increase uh, of the plastic waste each year, and also there has been a steep increase in the carbon production, carbon emission each year. And by using the catalytic cracking toward the plastic waste, we can create useful hydrocarbon which can be further reused for the production of the disturbed urea plant. Next. So regarding our problems above, what are our solution and designs? We will start with our block flow diagram, in which we will start with plastic catalytic cracking that is done in 400 degrees Celsius. It will produce the required hydrocarbon for steam reforming. Together with water, it will produce 3 molecules of hydrogen, in which 2 molecules can be used for Haber-Bosch process with nitrogen that we captured from the pressure swing absorption reaction from the air, and then the ammonia produced can be used for further urea synthesis. However, 1 molecule of hydrogen will be stored inside a tank, and it can be reacted in Sabatier-Senderens methanation with CO2 into CH4 or methane, which can further fuel steam reforming. We will start with our plastic catalytic cracking process. In the right is our polymer catalytic pyrolysis model, and it will crack the polymer of plastic into the hydrocarbon that is needed as a feed for the steam reforming. Now, the process also requires zeolite catalyst, also with 400 degrees Celsius of constant temperature. Next. And this is our steam reforming model. The steam reforming requires hydrocarbon that is gained previously, and with water it will form hydrogen and carbon dioxide. Now the carbon dioxide will be further used for urea production. However, the hydrogen will, as I explained before, one will be stored in the tank, and the 2 rest will be used in Haber-Bosch. Now we will use copper and zinc oxide based catalyst alongside with desulfuration and hydrogenation process before the reaction to keep the hydrocarbon clean. There are also 2 types of reaction happening in here, and it is high temperature shift around 680 Kelvin and low temperature shift in 500 Kelvin. Next. The next is our Haber-Bosch process. Haber-Bosch process happen in 400 until 450 degrees Celsius within 200 until 400 atm of pressure inside a fixed bed reactor between the hydrogen, 2 molecules of hydrogen and 1 molecule of nitrogen, producing ammonia. That 2 molecules of ammonia will be used in urea production, which consists of urea synthesis and high pressure recovery, medium pressure and low pressure recovery, vacuum concentrator, and urea drilling. Now first is our production and high pressure recovery. The production consists of the reaction between the ammonia and CO2, and it's forming ammonia carbamate, which will decompose into urea and and H2O. The reaction took around 15 hours if used copper-based catalyst, like in the screen, and the end result would be 45% of urea solution after high pressure recovery. Now, every pressure recovery is actually happening inside same type of decomposer, and it is falling film decomposer. The only difference is actually the pressure. Medium pressure recovery happen in around 17.4 atm, and low pressure recovery in 4.4. And because it has the carbamide decomposition, it is also helped with copper-based catalyst. And the last but not least is urea pruning. This is the simplest but also the fastest in the urea production. And it is consists of the urea concentration is being dropped from the top of the prill tower, which then the cold air will crystallize the urea, and it will drop, in which it is harvested and prepared for packing. Now, here's our one of our addition. The first is carbon capture utilization process. It consists of scrubbing, carbonate transfer, and calcification, in which the various type of chemical reaction, as mentioned in the screen, will be conducted. Next. And also, least but not least is Sabatier-Senderens Methanation, in which the hydrogen stored from the tank will be reacted with the carbon dioxide captured from the air from the various chemical looping that we that in the previous slides, and it will form into a methane through the exothermic reaction. And in the right is actually the process flow diagram. Next.
Okay, so after all of the process that have been explained in the previous slide, we are here to propose what are the reasons of this process can be implemented to alleviate the supply chain uh, problems in F&B industry. The target that we want to set economically is by we are using plastic waste of 80 tons per day with the 24 hours process with 20 to 20 cycles, and the target of 118.8 tons of product will be generated per day, and all of that in the case of the urea product will be set in 20,000 rupees per kilogram will be set will and that will set a gross selling point of 160.8 14 US dollar per day. We also put a target of our plant location, which is located at Palaran district at Samarinda, is Kalimantan, with several objections. With the first is located directly near with our next candidate of capital city of Indonesia, and also the productions of plastic waste in those areas are very potential, and also the land foundations is supporting for our type of project itself. And now we are present to you what are the trade-off, what are the risks, what are the impact of our process into our nearby to our environment. So the first is environmental risk. We have degradation of soils due to over farming, or also the acidification of the nitrification that happened to our process, and also degradation of fertilizer into N2O because we are using the urea, and also we also dealing with process safety because we have non-functioning catalyst, and also the impact of hover brush, and also the product which is have a probability of explosive, and also the toxic that probability that could be happen in the process itself. The last one will be talking about investment and operating costs, which will be talk about the equipment that we needed, also the amount of safety regulations of the various phrases that we need, and also various catalysts that we've been mentioned before. But all of that, we should see the bigger picture of why we should propose, why we want to propose this solution to all of you. We try to decrease our natural gas import dependency of our country. We try to increase our third world nations food security. We try to increase our national export surplus. And one of the main is we try to reuse our plastic waste, which is one of the most trending, one of the most biggest problems in our environment right now. And also all of that will be support will that our process will support the G20 circular economic agenda. So all of that impact also the production itself, which is in line with the government green agenda, which is also increasing national food resilience, and also being uh, being able to create a new source of fresh air of our food and beverage industry. We believe that our process will have to overcome, will help to alleviate the supply chain crisis in food and beverage industry. So this is our reference. Thank you for watching and thank you for listening to us.